Welcome to part 11 and the final part of the Chemistry IAS Edexcel Unit 1 revision notes. So this is the last topic, alkenes, before we get into Unit 2. But starting off very quickly with the alkenes, this is one of the most important topics again, along with topic 4. But yeah, let's begin. So 5.1, note the general formula of alkenes and understand that alkenes and cycloalkenes are hydrocarbons which are unsaturated. Okay, so what do you mean by this? Now, what is an alkene? Sorry, what is an alkene? An alkene is basically an unsaturated hydrocarbon. What do you mean by this? Unsaturated means, before lesson we saw that saturated meant carbon-carbon single bonds. Unsaturated means that there are carbon-carbon double bonds. So, for example, the simplest alkene is ethene. So again, we can use these, and this is the prefix, and then add "ene" as the suffix to form alkenes. Okay. Now that is what a alkene is. That's how it looks like. Let's say you have propene. This would be propene, or you can remove the double bond. It'll be here. That is still propene, and then fill out the the hydrogens. Okay. Now it's important to note that because this is a double bond, the carbon will bond to two others and one other here. Okay. Each carbon can only bond to four in total. Okay. Now, how do we name alkenes in more defined manners? Okay. Let's look at butene. Okay. And then draw the hydrogens. Okay. You'll not get a mark if you draw this. You need to draw the hydrogens at the end, but to save time, I'm just drawing this. This is not butene. If you call this in the exam, you get it wrong, because if you write butene, the double bond could be over here, it could be over here, it could be anywhere, okay? You need to specify. Since it's on carbon 1, it's in carbon 1 and 2, so you take the lower number, which is 1, and you write but1ene. Now, what's the alternative? If this carbon double bond wasn't here, and it was here, this is the second carbon and the third carbon, okay? So that would be but2ene. Alternatively, if it is here, this is the third carbon atom. Sorry, this is the first carbon atom, and this is the second carbon atom. You take it from the lower side, okay? So this will be but1ene again, okay? That's important to note. Now, what is the reason for, what's the general formula first? Let's look at that. We can see here there are two carbons, and there's four hydrogens. So C2C NH2N. For every carbon, there is two hydrogens. That is the general formula of an alkene, okay? It is CnH2n. Now, why do we get a carbon-carbon double bond in the first place? It is because of the carbon bonding through a sigma bond to another carbon, and then there are pi bonds. One pi bond forms a carbon, an extra bond, okay? So this is a pi bond. Let me use a highlighter, sorry. This is the pi bond and this is a pi bond. Together they form a carbon bond. So you'll have this carbon bond, the initial one, and you'll have a newly formed carbon bond to form a carbon-carbon double bond, okay? That's important to note. So we do not mention this as one pi bond. This is known as half of a pi bond, and you will have two of those. So you'll have half pi bond down here as well. Half pi bond, sorry. I don't know why I keep, okay, half pi bond. Wow, yeah, so when you have two half pi bonds, that is equivalent to one pi bond in total, and that will create an extra bond, okay? So this is the reason as to why there's a double bond, is because of the pi bond overlapping each other. They're two half pi bonds, which form an extra carbon bond, so the carbon-carbon double bond forms, okay? Let's move a bit more quick. 5.2, be able to explain geometric isomerism in terms of restricted rotation around carbon-carbon double bonds and the nature of the substituents on the carbon atoms. Okay. basically what we're supposed to know is you cannot rotate these carbon atoms cannot rotate, okay? Because of the double bond. In our previous question, we like for alkanes, okay? Let's look at it for alkanes first. You have CC, you have H, 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 Cl, Cl. Now, if this Cl wasn't positioned up and it instead came down, okay? So instead of up, it's down. We will still call this 1, 1, 2 dichloro ethane, okay? We'll still call it that. We won't call it anything else, okay? Now, this is because, and let's say it was reversed. The Cl went up and they were now on the same side. It will still be called 1,2-dichloroethane. Now, for alkanes, that is different though, okay? What do you mean by this? If you have a carbon-carbon double bond and you have Cl, H, H, and a Cl, these Cls are on opposite ends, okay? Meaning one is up and one is down. So what happens? You will get E and then 1,2-dichloroethane. Ethene, because of the double bond, okay? If the if the chlorine was on the same side, both of them up, you will form Z12-dichloroethene. Now, what is the reason for these letters? Why are letters coming in chemistry like this? The simple reason for this is because when you have a pi bond, you cannot rotate. For a previous example here, whether this there can be rotation along this, so this whole structure will reverse and the Cl will come down. But in alkenes, it is not possible because of the double bond, because of the pi bond specifically, okay? Don't say turning can't occur, rotation can't occur because of the double bond. Say rotation can't occur due to the double bond, due to the pi bond being present, okay? So wherever there's a pi bond, you cannot rotate. Limited rotation is there. Now, how do we remember which is which? E is basically, like if you look at the way it looks, okay? Z and E. The way I create this is Z is, if you look at it, it's in the, again, this is all tricks to try and remember this so that you don't confuse it in the exam, okay? Z is literally in the opposite ends. So in my mind, if Z has opposite ends, that means that Z, I add some opposite rule and I tell myself that Z should be for this Z because it's on the opposite ends, the chlorines, okay? So I switch it in my head, okay? I know it's confusing and I'm just saying create your own sides, okay? But yeah, let's just look at another way of trying to remember these things. My examples are not helping, but yeah, Z. Well, I'm not gonna give an example because I don't have an example, but just know E is for opposite ends and Z is for the same side, okay? If you don't want to use the alphabets, then you can use cis and trans. This is more easier to remember. Trans basically means that you have switched. So trans is for this because you have switched. And then cis automatically becomes this, okay? So you can write this as cis 1,2-dichloroethane and this one as trans 1,2-dichloroethane, okay? Yeah, we can take that. Oh, we've actually done that here. EZ and the cis trans naming as well. We've done that. Next up. Oh yeah, one more thing that I've not mentioned. How do you name if you have multiple elements, okay? Let's say you have a carbon-carbon double bond and you have bromine here, fluorine here, chlorine here, hydrogen here. Again, my notes are all, these are not my notes, they're notes from online, but if you want, just do research and revision and you get the same. This content is all online. I'm just trying to, when you're revising, again, it's a tip. Just try and revise from, use your notes at school, but also in addition, use notes online. And again, if that doesn't make sense, then, try looking at videos. My videos might not help majority people, but, for the few that it does help, use what helps you. That's what I'm trying to say. Anyways, how do we look at this now? What do we name this? This molecule is called it's a Z isomer, okay? Why is it a Z isomer? Z is when both are top elements, okay? Because we look at the relative, we look at the mass, okay? So if you look at the molecular mass of bromine in the periodic table, it is greater than the molecular mass of chlorine, and chlorine's molecular mass is greater than fluorine. So these two are the main elements. You look at the first two, okay? So bromine is up and chlorine is up. So this will be a Z isomer. What's the name of it? Z. And then we have bromo, we have chloro, and we have fluoro, okay? We look at it alphabetically. Which one comes first? It's bromo, so be bromo. Again, we have to add numbers. 1, bromo. 2, chloro, because C is before F in the alphabet. And then back to 1, fluoro, okay? Fluoro, ethene. This is ethene, okay? This is how you write the name of it. Write it in all one line. I'm coming, one line below because I don't have space. But yeah, that's how you name that, just to come back to that, okay? Continuing now. Okay, now when you have alkene, let's look at 5.4. Describe the reactions of alkenes with hydrogen. Let's look at that first. When you add an alkene to hydrogen, this is called hydrogenation, okay? Carbon-carbon double bond. Let's look at ethane because it's the most simplest. When you add hydrogen to this, what do you expect? Now, I would expect that you would form this, okay? The hydrogen is used up and the carbon-carbon double bond is broken to form an alkane, which is ethane, okay? So alkene plus hydrogen will give you alkane, okay? That's what we have to know for that. But it does have a catalyst, as said. The catalyst for this is the nickel catalyst, okay? So nickel catalyst, okay? Try again to keep ways of remembering this stuff. Alkene plus hydrogen will give you alkane with the presence of a nickel catalyst, okay? Yeah, so continuing with that. That's the first one. Number 2, the addition of halogens to produce di-substituted halogen or alkanes. Now, when you add a halogen, by the way, one more thing I have to mention is this is known as an addition reaction. It's called hydrogenation, okay? But it is an addition reaction, okay? Specifically, it's an electrophilic addition reaction. Why is it electrophilic? Electrophilic. Electro basically means, we covered this in a previous video, but electro is electron liking, and philic means, electro is just electron, and philic is liking, when you like something, okay? Philic, yeah. Now, in the carbon-carbon double bonds, there's richness of electrons because there's many electrons fit into that carbon-carbon double bond. So hydrogen, obviously, will like to attack. So it's an electrophilic addition reaction, okay? That's what we have to know, okay? So it'll attack there and it'll get there. But when you're drawing the reaction mechanisms, you actually draw it like this, not the other way. But yeah, anyways, for halogen alkanes, it's a bit different. You can form monosubstituted halogen alkanes, or you can form disubstituted halogen alkanes. What do we mean by this? So when you have a alkene plus Br2, you can initially form, so you'll form 1,2-dibromo. Let me just draw this to make more sense of it, okay? 1 second. Okay, so when you have a carbon-carbon double bond, this is a reaction mechanism that we have to know, okay? This is ethene, and you have Br. Under the presence of UV light, Br will break, okay? But we do not draw it here. what we draw is from this electron richness. Remember, arrows always go from negative to positive. So this part will be electron rich, so it'll be negative, okay? This carbon-carbon double bond. So we draw an arrow from this to this, to the bromine, and we draw an arrow from the bond to the other bromine. What do we form here? We'll essentially form CC. I have not drawn that correctly. CC, HH, BR, H, H, okay? And a positive, okay? And then we'll form a Br minus. Now this is a nucleophile. Why is this a nucleophile? Because it is negatively charged. It will be attracted to the positive, so it's called a nucleophile, okay? So this now, again, arrows go from negative to positive, and you will essentially form, again, do this on one line. I'm just doing it on two lines because I don't have space. You'll form 1,2-dibromoethane, okay? So this is how you form ethane, dibromoethane, 1,2-dibromoethane. But yeah, that's what we have to know for that. This is complete substitution. What do you call incomplete substitution? It's basically when we do not have this. Oh yeah, one more thing, add dipoles, positive, delta positive and delta negative. Delta negative will always be the negative charge, just choose one, but essentially make the delta negative charge the one that is negative at the end, okay? One more thing. If we have hydrogen, HBr instead of Br, same reaction, but you will form 1-bromo ethane, okay? Keep in mind why. So it's because HBr, will substitute 1. In this case, you cannot choose which one is negative. The Br will always be negative because hydrogen is the positive, more electropositive than the bromine, okay? You're not supposed to know why in this case, but yeah. So we've talked about dye substitution as well. Now, addition of hydrogen halides. We've actually talked about that. So that second example I gave was monosubstituted. The before one, when we did 1,2-dibromoethane, was dye substitution of alkane, of a halogen. And the second one that we did, the one we recently did here, will be a monosubstitution, okay, of a halogen. The next part, addition of steam in the presence of acid catalyst to produce alcohol. It's literally written here, okay? When you add a alkene in the presence of steam is basically H2O, but in gaseous form, okay? So H2O. Let's just draw this better. H2O. Okay? What you'll essentially form is, this will be delta negative, this is delta positive. This will go here, and this will go here. So again, we'll form, it's the same reaction mechanism essentially, okay? But the carbon-carbon double bond breaks again, and you will essentially form a carbocation here, and OH minus will attack here, and you'll form an alcohol. Let me just draw this here. You'll form an alcohol, okay? Again, this is in the presence of an acid catalyst, okay? The acid is the catalyst. I don't need to mention that last part, but yeah, the acid is the catalyst, okay? Yeah. Oxidation of the double bond by potassium manganate 7 to produce a diol. Now, for this one, it's a bit different now, okay? We do have so what is the potassium manganate 7? It is basically KMNO4, okay? KMNO4, okay? Now, what is a diol? One second. Yeah, sorry. What is a diol? A diol is essentially something that has oxygens attached to it, okay? So it's like a diol. So it's, how we say alcohol. So this one will have two OHs, okay? When you add alkene to the KMNO4, again, KMNO4 has KMNO4 minus. This is basically what oxidizes the alkene. Sorry. You will form what we call a diol, okay? You'll form a diol. Let's take an example. We're using the most used example, the simplest example, sorry. But yeah, just figure out how to move it around, okay? Plus 2 OH. You will form C. This is what KMNO4 gives you. This is not KMNO4, but it's what KMNO4 gives, okay? So again, if you're told to write the reaction, don't write this, write this. If you're told to write the reaction between alkene and potassium manganate 7, okay? This is what you form. What is this called? This is called 1,2 ethane 1,2-diol, okay? This is what it's called, okay? Ethane 1,2-diol is what this is called, okay? So yeah, that is what this is. This whole thing done. Know the qualitative test for C2C double bond using bromine or bromine water. Okay, bromine. What is the color of bromine? Now, bromine has a dark. I'd want to say that the color is like red brown actually. But yeah, bromine's color will, when you are testing for the presence of an alkene, it's important that we use bromine, either bromine, or we use bromine water, okay? Now, we've talked about this before up here. Here, bromine water, bromine is Br2, we know that. Bromine water is HOBr, HOBr. So it has water molecule, like OH minus, a part of a water molecule, and Br, okay? So when you have an alkene, let's use the simplest one again. This is ethene, and you add bromine. The bromine will break the carbon-carbon double bond, and what you'll form is you'll form 1,2-dibromoethane, okay? Now if you use this, you will form the same thing, just OH here, okay? So why is this a test for, why is this a test for alkenes? It is because when you break the carbon-carbon double bond, you essentially remove the bromine and the bromine water, okay? But how do we know what the positive test is? It's because you will see a color change. When you use bromine, the red-brown color of bromine, will decolorize. Bromine water has like a brownish color, so the brown color, again, will decolorize. This is essentially the test for alkenes, okay? That's the qualitative test for alkenes using bromine and bromine water, okay? There are more tests, but you're supposed to know these for Unit 1 only, okay? Be able to describe the mechanism giving the evidence of electrophilic addition of bromine and bromine hydrogen bromide to ethene. We've talked about this actually. Electrophilic addition, we did it above here. Sorry, we did it over here. So we talked about this electrophilic, and then because it is being added to the, it's called electrophilic because you form an electrophile, which is, you form H plus, which is the electrophile, which is added, okay? And why is it called addition? Because you are combining two reactants, which is ethene and HBr, to form one product, okay? So again, you'll be asked that in the exam. You'll get a question saying, this reaction is a electrophilic addition reaction. State what is meant by electrophilic and state what is meant by addition, okay? So you have to know what is what, okay? And we actually talked about the nucleophilic addition as well, I think. Let me just check. Using bromine we talked about, and using hydrogen bromide we talked about, okay? Yeah, but here they say you're supposed to know the reaction to propene. Propene is basically just an extra. It's basically just this. So it's the whole mechanism for ethene, but just instead of ethene, draw this, okay? Everything else is the same there. Yeah, again, curly arrows start from the positive to the negative. Again, so in simple terms, it starts from the bond to the lone pair of electrons. Electrons are negatively charged, or just from positive to negative, okay? Yes. We can take that. Oh yeah, let's just see this last sentence really quickly here. Stability is dependent on the carbocation formed. We mentioned it up here. This is what you call a carbocation. It's because, what do you call a carbocation? A carbocation, let's take alkene, ethene again, H, 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 H. When you add a hydrogen here and you break this bond, you will form this. So H, 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 and a positive here. This is known as a primary halogenoalkane, okay? Sorry, a primary carbocation. So this is a carbocation. Why is it called a carbocation? Carbo because it has carbons, you know, what we talked about before, hydrocarbon, yeah? So we call it a carbo because the carbon is a cation, okay? This only applies to these kinds of, what is it called? It only applies to organic molecules, okay? Which are, now this is a primary carbocation because only one methyl or one carbon is next to the main or the carbon with the charge, okay? What do we call, how do we draw a secondary one now? If you have propene and you break this bond, then you'll have a secondary carbocation. Two methyl groups are against the, you know, the carbon plus is in between of two methyl groups. This is a secondary, and how do we form a tertiary? This will just basically be this. H, 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 H. Ignore the, yeah, okay. Yeah, this is the tertiary carbocations because three methyl groups are attached to the carbon cation, okay? Now, in terms of stability, which is the most stable? It is the tertiary carbocation. Why is it the most stable? When you have the three methyl groups, let me draw this in a simpler way. When you have the three methyl groups, each methyl group pushes a force to the carbon with the cation. This makes it easier to attract electrons, to attract the negative charges, okay? So this will be easier to attach. That's why we call, so it's basically allowed to stay, okay? What do you mean by this? When you form a tertiary carbocation, it is less likely to break down than if you had formed a secondary carbocation or a primary carbocation, okay? In simpler terms, tertiary carbocations are the most stable because of the three methyl groups surrounding the carbon cation, okay? This is due to the pushing effect of electrons. That's all we're supposed to mention in that phrase, okay? Yeah, so we can take that. Next part. Be able to describe the addition polymerization of alkanes and draw repeating units. So let's take a big alkane for this one, okay? And again, I'm just gonna draw these like this, okay? Now this is what we call as two, not that, sorry. 1, 2, 3, 4, 5. They're five, so it'll be pentene. And since this is located on the second group, not second group, this is the first carbon, second carbon, third carbon. So the least carbon will be the second carbon that the double bond is attached to, so it'll be pent-2-ene. Now, pent-2-ene, if we want to make it into a polymer, we have to draw this in a better way. So start with a carbon-carbon double bond, and then go on the each sides. You'll have a CH3 on this side. This is this. So bring this up, and then you'll have CH2, CH3. Bring this up as well. CH2, CH3. And then this hydrogen, we can bring, okay, I made a mistake. We can bring this down actually. Yeah, so let's just rewrite this. So you bring this down, you have CH3, this is this here. And you bring this down, you have CH2, CH3, this is this here. And then you have the hydrogens up top. Now, if you want to form a polymer, remember a polymer is many monomers joined together. You break this bond and you extend this like this. This is what we call a repeating unit. It's a monomer, okay? That's how we form a monomer from a alkene, okay? So yeah, we can tick that. And when we're asked to deduce the monomer from the polymer, take this and just add a carbon bond and remove this here, okay? That's how we form the alkene. Understand how chemists limit the problems caused by polymer disposal by developing biodegradable degradable polymers, removing toxic waste gases produced by incineration of polymers. Okay, now one important thing about this is it's not tested as much. I've actually not seen it being tested multiple times. I've only seen it once, but we have to know this nevertheless. It can be asked, but it'll come as a 2-mark or a 3-mark question. So, why are some polymers good? You know, why? So, if you are asked about the biodegradable polymers, why do people use these days over regular polymers? It's because this is biodegradable. And then they'll ask you what is meant by biodegradable? Biodegradable means that the polymer will naturally break down in the environment at a quick pace, okay? And what if these polymers are not biodegradable? They're just polymers, okay? Now, if they're just polymers, they have to be recycled to prevent harm to the environment, okay? Because regular polymers like plastics, they will just stay in the environment and they will keep building up and taking up landfills, and they take many years to break down, way too many years, okay? Now, that's another way of looking at it. Another way is plastics can be burnt, they can be incinerated. That's the word that they use. Incinerated is basically being burnt using oxygen, okay? But they release toxic gases. Toxic gases are released. So it is not a viable way of disposing of polymers. Instead, polymers should be recycled. That's all we have to know about this topic. Basically, that regular polymers like plastics, they are incinerated and they produce toxic gases, so that shouldn't happen, and instead they should be recycled. And biodegradable polymers are good because they naturally break down in the environment, okay? So that is for unit, wait, we can actually take this as well. Yeah. Okay, sorry. Yeah, so this is all for the unit 1. We look at the practicals in the unit 3 because these practicals that we've skipped throughout the unit will come in the unit 3. So when I'm making the unit 3 videos, I'll cover these practicals. But yeah, in the next video, we'll look at we'll start unit 2 chemistry.